Scientific Sue. Welcome to UCD's very first virtual festival. And we're hoping it's going to be the last virtual festival because we want to invite you all back on campus this time next year. And a very special thank you to Intel who are funding and supporting this show next year. Over the next 3 days, we're going to be looking at my really rubbish show. And today, we're going to be looking at what litter is and going into the science of dissolving and floating and sinking. Tomorrow, we're going to be looking at plastics and polymers and the litter there. And lastly, on our third day of the festival, we're going to be looking at a specific type of litter called graffiti, and some really magical chemistry is going to occur there. So again, I'm Scientific Sue, and I think it's time we moved on to our first set of experiments. Before we do any of our dissolving experiments that we're going to do next, we have to really look at some of the litter that we find on the streets. And I'm going to pull the litter out, and I want you to shout out whether you think it's going to stay in the environment forever, which means it will never ever disappear, whether it's going to be there for maybe 2,000 years, 20 years, 2 years, or just 2 months. Okay, so let's have a look at some of the things that I've picked up. So I've got a whole range of cups. Polystyrene cups, plastic cups. I've got this kind of cup here. I've got food packaging, polystyrene, or a mixture of cardboard and plastic, or just cardboard. I've got some peelings of fruits, bananas and oranges. Oh, there's another paper cup with a plastic lid. I've got aluminium can, I've got a plastic bottle, I've got a glass bottle, a baby's nappy, a plastic bag, and a paper bag. Okay, now, none of these should have been on the streets. We should have all put them in the bin. So as I'm talking, I'm going to throw them into my bin. Right, okay, so 2 months. What did you think would stay in the environment, dissolving down, breaking down for 2 months? Let's see if you were right. Paper bags. Anything made from paper or foodstuffs will disappear. So a paper bag can go, and my banana can go as well. Right, what's next? 2 years. Which of those things here did you think could take up to 2 years? Let's have a look. Still to do with food, cardboard, thick cardboard food packaging, and orange peel or banana peel. It all depends on the weather. If it's really dry, and these will stay in our environment for quite a long period of time, but eventually they will break up. Anything made from plants and things will break up eventually. However, we're going to have litters that will stay around for 20 years or more. So what we've got here then is we've got our plastic bag, very thin plastic, and I've got a plastic cup, and I've got this cup. Now I love this word. Look, can you see it? Biodegradable, compostable. It's telling us it's grown from plants. It's like this one here. Oh, it's gone in there. The paper one is going to be gone. It's gone. No, this one is lying. It's covered in plastic. It's all shiny. 20 years before this one will disappear. But this one, it's not plastic. This has been made from a new material. It's been made from plants, and it is biodegradable. It will break down. Now, what have we got next? Up to 2,000 years. 2,000 years. Did you guess right? Yeah. Aluminium cans. Aluminium is a very unreactive metal. So steel, it takes about, 40 to 45 years for metal cans to go because they rust. These ones not. So up to 2,000 years. And what else do we have there? These bottles. Because of its thick plastic. Now, the last one. Never, ever, ever to disappear. Glass bottles. Here we go. And nappies. Not the wrapping of the nappies. It's something inside them, which I'm going to talk about tomorrow in our plastic polymer session. Right, food packaging, cardboard and plastic. Whenever we're going to be recycling, we have to remove the plastic first. That goes into the bin, then the cardboard can be recycled. Plastic lids, polystyrene cups, but that's not all that we're worried about. I'm not sure if you can see this. Can you see all those little kind of holes there? Our animals try to eat our litter. And we're going to talk about what happens to the animals when they do. But enough talking, let's do the first hands-on experiment. Now we're going to look at dissolving, and this is one of the experiments where I put up a list of things for you to maybe get hold of so that you could actually do this with me. So we want to find out, when I'm talking about things being biodegradable or disappearing in nature, we mentioned that word dissolving, and I've got a couple of materials that we're going to be looking at. So one of them is toilet paper. Okay, so I'm just going to take two small sheets of toilet paper. I'm going to put that there, and the other one is a wet wipe. Now you can look at anything that you want at home to find out if it dissolves, and you can carry on exactly doing this type of experiment. So what we're going to need are 2 containers which have lids that we can put on that are going to be very, very tight. They're not going to allow any of the liquid to escape when we start to shake them. Okay, so we're going to have to shake them really, 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 really violently and fast. Now, I'm going to put them in together. So if there's 4 of you in the family, you can all 4 of you do this. Or if there's only 1 of you doing the experiments, you're going to have to do 1 at a time. But each time we're going to do it for 10 seconds. So in the yellow water, I'm going to put in the toilet paper. There we go. And in the blue water, I'm going to put in my wet wipe. And I'm going to put the lids on. And then, making sure they're going really tightly, otherwise I'll get soaked. And then we're going to shake for 10 seconds and we're going to see what happens. Are we ready? So, what's in the yellow one? What's in the blue one? Okay, let's find out. Ready, steady, go! 10! Stop! That was a bit difficult for me. They nearly fell out of my hands. Now, let's have a look and see what's in here. So that was the toilet paper. If I put my hand in, can I get hold of anything? No. It's broken down into tiny, tiny pieces, which are now floating in amongst all of the water molecules. Let's have a look at the wet wipe. Well, it's a bit bubbly because of the soap that's there. Should we see if it's changed size at all? Let's open it out. Open it out. Look. Nothing. Nothing. Very thick. Oh, it's even really difficult for me to try to pull it. The force there. Oh, I can't even break it with all of that force. Yeah. So, at home, in the toilets, we only put 3 things. Toilet paper, pee, or poop. Nothing else. Nothing else. Because the other things, they don't dissolve. And it could block up the drains. Now, we have another problem with all of this litter that doesn't dissolve. So this time we're going to try 2 different materials, okay? And I'm going to put them into these jars. So I kind of have the yellow one there, and I've got a blue one here, okay? And these are going to be 2 lakes that are close to me, because I live in Northern Ireland. So this is going to be Lough Erne, and this is going to be Lough Neagh, okay? In fact, I'll just turn that around, and so that we can see them there. And into them, I'm going to put 2 materials. They have the same job. They're called packing peanuts. And this one here is made from cornstarch. They look a little bit like the What's It sweets that we have. And these ones here are made from styrofoam. So it's polystyrene fluffed up with lots and lots and lots of air. And I'm going to put them in to my lakes. And let's see, do they float or do they sink? So 3, 2, 1. not sure how long they'll float for, but while they're floating, all of a sudden, this little fish has come along. And the little fish is going, ooh, well, that looks like food. And it starts to eat this food. And then it swims away again. But on top of this lake, a little birdie comes along. It's springtime. Flying along, dives down, gets some of the litter because he thinks it's food. It's going to go all the way back to its nest. It's going to find its baby chick. And it pushes the food into the chick's mouth because they're going, feed me, feed me. So they're going to go back and they're going to get more of this food for their baby chick. They're so happy they've found all this food. And they push it down into the mouth of their baby chick. Should we find out what's going to happen? Okay, ready. Put the lids back on again. Got to make sure that they're on nice and tight, otherwise we end up getting soaked again. This one here has been made from a plant material. This one here has been made from plastic. Countdown from 10 again. Are we ready? Here we go. Go! Stop! Let's look at this one first. This one first. The fish is going to come along. Oh. Where's all the food gone? I've got lots of bubbles, but there's no food. It's broken down even more than the toilet paper did, but we can still see some tiny, tiny particles. So that's now going to be food for the tiny, tiny animals. However, this one here, it's still floating on top. It hasn't changed size, and it has not broken up. This will stay in the environment for hundreds of years. And because it doesn't dissolve, we can't digest it. And that means when we put it into the mouth of the chicks, and it goes down the tubes, it blocks the tubes, and the wee chicks can't eat. And then they die. So it doesn't matter how small the litter is. If it's really tiny, the birds will pick it up and feed it to their chicks. So anytime we drop anything, keep thinking, where will it go? What will it do? So for the next part, we have to go back in time. For me to explain what's going on, I have to go back about 2,100 years ago. And we're going to go to ancient Greece, and we're going to find out about a scientist called Archimedes. And the reason we're going to do this is whenever we've got our litter, we've found out that some of it will dissolve and some of it doesn't. And the litter that doesn't dissolve, well, it can go on a journey. It can be kind of taken away by the wind, or it can be taken away by moving water in drains or the rivers or even in the seas. Some of your litter could go from here all the way over to Australia and vice versa. So we want to find out how that happens. And to do that, we really have to kind of find out a little bit of this kind of weird science. Now, I finished with dissolving, so I'm going to start this session with a little bit of dissolving first. I've got a measuring cylinder here. It looks empty, but it's not. I've got it filled to the brim with water. I'm going to very, very carefully lift it up and place it into this measuring jug. And then I'm going to put in a little tablet. I love them. They're bath tints. And so sometimes we kind of have dissolving tablets that we might take for a headache or for our vitamin C intake. So I'm going to put this in, and at the moment the water's clear, but when that goes in, very slowly we're going to start to see a colour appear. And I'm going to put a second one in because I want this nice big bright colour. And very gradually we're going to see the yellow move up through the tube. The water molecules are moving. So what I want you to do is I want you to start clapping your hands slowly. So we've got cold water, they're going to move around, have a little journey, slowly. Maybe you want to move around the room slowly, okay? And then bump into your mum or dad, or bump into your uncle, or bump into a chair, I don't know, but very slowly, so you don't get hurt. But when we go faster, so if I heat it up and give it a bit of energy, go clap faster. Keep more, faster, 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 faster. Oh! Did you feel that extra force and pressure? So the water molecules, they bash into these crystals. So I want you to imagine that we've maybe built a wonderful groovy car out of Lego. And then if we kind of get a popper gun, we can fire the little balls at the car, and if it hits it with enough force, the Lego pieces can fall off. Till eventually our car is broken down to all of the blocks we made it from. And that's what's happening here. So the water molecules are hitting that tablet. The little pieces are coming off. And then the water molecules are just kind of pushing them around, just like I can push this around, okay? And remember, we've got a force called gravity that pulls everything down. So if they're moving up and spreading through, they have to be hit by something to push them up. So now we've got that yellow color. That's going to help me with the next part so I can see what's going on. So when Archimedes was alive, they did lots of mathematics, and they were able to work out the volume of cubes, like a dice, or of a round ball. But if they had a weird shaped object, like this is a weird shaped object, they couldn't find the volume. And he used to think about these problems, and then one day he took himself off to the baths. And the baths, it would have been nice and big and round and filled to the top. And when he got into the bath, the water went over the edge of the bath. And normally you'd be panicking about the water going everywhere. He didn't. He screamed out, "Eureka!" So that was his Greek word of saying he'd solved a problem. He'd found the answer. And he realized that the volume of water that went over the edge must be the same volume of the shape that went into the bath in the beginning. So when we do these experiments in school now, we kind of call these displacement cans or eureka cans because of he kind of came up with that idea. Now, what I've got here is a jug. And unfortunately, it's too big for me to work out the volume, that small volume. So I'm going to use another measuring cylinder. So we're going to pour this in there, and hopefully, because it's narrower, it's going to allow us to find out more clearly what the volume is. So if I kind of do that, I'm looking at a volume of 20 milliliters. Can we see that? 20 milliliters. Now that we've got the volume, we can also find out the mass of the object, because they did have weighing scales there, not kind of electronic ones like I'm going to use. They used to kind of have little scales where they would balance a weight on one side with a known weight on the other. Okay, here we go. Now, so I'm going to use these scales here. So when I press it on, okay, we're going to go to 0, at 0, and I'm going to stick this on there, and this has a mass of 49 grams. Okay, now with my knowledge of the mass, the amount of stuff that's there, and the knowledge of the volume that it takes up, I can now calculate a quantity called density. Density lets me know I've got a certain amount of stuff in a volume. And the more stuff that goes in that set volume, the more dense it becomes. And so let's just say that this is 50. And we've got 20. So if I divide 50 by 20, what number do I get? That number is going to give us its density, and its units are going to be grams per milliliter. And what you can go and do now is find out volumes of lots of weird things in your house using this displacement method, use the scales, and then you can find out its density. And then you're going to be able to work out if it will float or sink. The density of water is 1 gram per milliliter. If your density is less than 1, say 0.5, it's going to float. If your density is more than 1, it's going to sink. And if it's equal to 1, it's going to be suspended. So we're going to look at that right now. So with Archimedes' help, we now kind of have a small understanding of density. And you may have heard of a word of buoyant or buoyancy. So if we're going to go on a journey in the oceans on a boat, we'll put on a life jacket because it's going to be buoyant. And buoyancy is affected by density. So you don't want to jump into the sea with a life jacket filled with lead, one of the heaviest metals, because it's going to pull you all the way down to the bottom of the sea and you'll die. That's not good. So you want to fill your life jacket with a material that is lighter, has a smaller density than that of water. Now what I've got here is I've got 2 balloons, one pink and one blue. Now what do you think is going to happen when I put them into this little pond of water here? Okay. Got the idea? Okay, let's go. 3, 2, 1, plop. Did you see the blue one bounce? Now this one here is floating. It's buoyant. It has a density smaller than that of water. So it's smaller than 1. Now, how am I going to be able to find out the volume of something that floats? So I'm going to show you a little trick that he used to do as well. Now, the blue one, it did sink first of all, but now, can you see that it's just floating just underneath the surface of the water? So we say it's suspended. So basically, this is a little water balloon. So the balloon is very, very light. So it's pretty much, its density is very, very similar to the water that we have here. So I'm going to take that out now. If I filled this to the top, and if I had a tray underneath, then using this string, I could pull the balloon underwater. And then the volume of that ball, I could measure, as I did with that weird looking object, by the amount of water that goes over the top. Now watch this. It kind of gets pushed up. So it's pushed up by the water, and we call that pushing force upthrust. So it's got a weight force down, okay, and it's got a pushing force up. Which of those two do you think is largest? Which one is winning this battle? Is the weight force going to keep it down, or is the upthrust going to be bigger and push it up? Yep, you're right. So being buoyant is good, because even if you go under, that upthrust is going to push you up out of the water. Now, this is a fluid. This is a fluid as well. Fluids can be liquids or they can be gases. And just like liquids, we can have oil and honey and water. We can have different gases. So I've got a gas here. This gas is called helium. And I can use it to change the shape of my balloon. Perfect. I filled it with a gas. I'm going to tie this off now. And using my hands, I'm going to push it down, push it down, push it down, push it down to nearly the bottom of this ocean of air. If I take my hand away, whoop, it floats up again. Right, oh. So it's exactly the same as what we've got here. I kind of pull it down, and then we're going to have an up thrust from the gas molecules pushing it upwards. Step sideways here and get my balloon back again. There we go. So whenever we're talking about forces, we're going to have pushes and pulls. Weight is a pulling force due to gravity pulling things down. Upthrust is a force that pushes things upwards. Now, remember, I had this here. When it went in, it kind of just hovers there. This is what happens to a lot of our litter. If it ends up in the oceans, its density is very similar to the density of the seawater. So we don't see it on top, and it's not on the bottom. It actually moves. It goes on the journey that the oceans move. But unfortunately, we've got lots of fish that are sharing that area, and they, just like the little bird and the little fish we saw earlier, they eat that litter. Some of the animals need to go up to the top of the water like a turtle to breathe. But if it eats this litter and it makes it heavier, more dense, then it can't get up to breathe. And unfortunately, they don't live. So we've got lots of fishermen look for these little turtles to try to save them, and they operate on them and they save their lives. If we didn't drop litter, we wouldn't have to worry about that. If we drop litter, we have to think, where will it go? What will it do? Can't believe we've come to the last set of experiments. Now, I've talked about moving air and I've talked about moving water. How does it get to move? How do we form the wind and the ocean currents? So I've got another balloon here, because this one here is bought by a lot of people. It's released for wedding ceremonies or for peace ceremonies or whatever. And they don't release one, they release hundreds. And when they get released, they're going to go upwards. So let's remove one of these weights here. Let's remove one of these weights. There we go. They're going to move upwards. And as soon as they get into the atmosphere, it's going to get really, really cold. And the plastic changes from a stretchy material into a brittle material, and it bursts. Now, by putting these little pumpkin seeds on, hopefully I am going to increase its mass. That increases its density, and it's going to start to come down to Earth. Now, I'm not going to change anything now in terms of mass. The mass is going to stay the same. What I am going to do, though, is I'm going to heat this gas up, because we have the sun. And some parts of the world have more sunshine, more heat hitting the surface than others. And what happens is, when we get that heat, the gas expands, becomes less dense than the air is in, and it floats upwards. And then as it cools down, it kind of sinks. So what we're going to do, we're going to heat it up using this really cool piece of physics equipment, my hairdryer. I haven't completely filled it with gas. Okay, I've still got a little bit of room there. And then as I heat it, I should start to feel that gas inside expanding outwards, taking more space. So you won't be able to hear anything because this is going, so I'll start nodding if I feel that. And we're going to have a countdown from 10, and then I'm going to let it go, and then we'll see what happens. Okay, so here we go. Here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off. Oh my goodness, it's going upwards. It's going upwards. And then the heat source isn't there anymore. That gas is going to cool down, and the space it takes is going to get smaller. This is my Hoberman sphere. So let's have a look at this. Okay, you ready? Takes all that extra space. So what we've got then is, I haven't changed the mass. All the mass particles are there. And as I heat it, the gas molecules, they want to move faster, so they push harder and they take up more space. When it cools, then they're not moving just as fast. They don't hit the sides of the balloon with just so much force, and the gas will contract, the volume gets less, we change its density, and it sinks down again. So at the moment, it is there. So I'm going to move on to another experiment, and hopefully by the time I finish this one, this will have cooled down enough that it will start to sink. And if you see it sinking while I'm doing the experiment, shout out, let everybody know you're seeing it sink. Now, in 1992, there was a big disaster for a toy company, okay? And this toy company had 28,000 little kind of rubber duckling toys going from Hong Kong to America. But there were storms in the sea. Now, I'm going to have to make some sea. And because Some countries like Greece, they're going to have hot oceans because the sun. Others, the Arctic, the water's going to be cold. So I've coloured them cold blue and the hot water is yellow, just so that I know which is which. Actually, you can see the steam, can't you? And in those seas then, the big carton of these rubber ducklings ended up going overboard. And over the last, was it 92, 1002, 1012? So we're looking at 30 years. These ducklings have turned up, not just in America and not just in the China Seas. They have travelled to Scotland, to Australia. They have travelled, I don't know, to Newfoundland. They've travelled to Argentina. In fact, they have travelled to every part of the world. And this has been really important science for the scientists that study the oceans, oceanographers. And what we have then, I'm just going to move this a little bit there. There we go. And I've got my little rubber ducklings. Here we go. So they are going to be in, what is it going to be, hot or cold? I'm going to put it in the cold section there, okay? So they're floating away. Now, because they've turned up, we've still got 2,000 missing, so we can still kind of look for those 2,000. Watch what happens here. Wowee. Got the stormy seas there, and our little ducklings, they're kind of still floating because their density is less than the density of the seawater that they were in, and they're going on their little journeys. Can you see down here? The blue water, the cold water, has sunk to the bottom. The yellow water, the hot water, has risen to the top. It's expanded, its mass is less. And where the two of them meet, we're going to have warm water and we end up with that colour green. So, what we have then, exactly the same in the air, we have with the water. When the water is heated up, it expands and it takes up more volume, its density becomes less. And as it cools, its density increases because the volume increases. So let's kind of all do this here. We'll start with your hands below. So as we get hot, it expands, lift our hands up, and there we go, it rises, and then as it cools, it contracts and it falls. And this is what causes the wind. When a cool air comes in, takes our litter on a journey, and it causes these wonderful ocean currents, which can take litter from one place to another place. Right, my room must be quite warm because of this balloon here. Oh no, it got stuck at the top there. Here we go, it's sinking down now. It's sinking down. So you have just seen Scientific Sue's really rubbish science show. Thank you so much. So hope to see you at UCD Festival next year on campus as opposed to being virtual. And a huge, huge thank you to Intel.